Our original definition of the derivative involved taking the limit of a so-called difference quotient at x equals a. This difference quotient can be understood as the slope of the secant line at x equals a, and we saw that it could be written as f of a plus h minus f of a all over h. But this isn't the only way to write the difference quotient. For example, if we define a new variable x to be x equals a plus h, then the difference quotient can be expressed in terms of this new variable x instead of h. In particular, because a plus h is x, we can replace the first term in the numerator by f of x. The other term in the numerator doesn't involve h, so we can leave it alone. In the denominator, we just have a term of h, which we could write in terms of x. In particular, solving for h in the expression of x, we find that it's equal to x minus a. This means that we can replace the denominator term of h by x minus a. Now, the derivative is the limit of this quotient as h goes to 0, but since we've written everything in terms of the variable x now, the derivative can become a limit where x goes to something. Looking at our expression of x, we realize that as h goes to 0, x tends to a. This means that the derivative can be written as the limit of this new difference quotient as x goes to a. In other words, this new limit, if it exists, is equal to the value of the derivative at x equals a, that is, f prime of a. Besides differentiability at x equals a, another property about the behavior of a function at x equals a is continuity at x equals a. Recall that geometrically, continuity means that the graph can be drawn without lifting your pencil. And algebraically, it means that the limit of f as x goes to a is equal to the value f of a. It turns out that this property of being continuous automatically follows from the property of being differentiable, in the sense that a function which is differentiable at x equals a will always be continuous there too. Let's try to prove this result. To do this, we should start by assuming that f is differentiable at x equals a, and we'll try to show that f must then be continuous there too. Now, to show that f is continuous at x equals a, we have to investigate the limit as x approaches a of f of x. Before, we saw that algebraic manipulation could be a useful tool in investigating limits, provided we can perform the right manipulation. The trick in this case is the following identity, which relates the function f of x to the difference quotient. Namely, we could write f of x is equal to the difference quotient times the quantity x minus a plus the value f of a. The reason this expression is valid is because if we look at the right-hand side, when we multiply the difference quotient by x minus a, we obtain just the numerator of the difference quotient, which is f of x minus f of a. And upon adding f of a to this, we'll certainly obtain f of x, which is the left-hand side. Now, one important thing to note is that this expression of f of x is only valid for x not equal to a, because at x equals a, the denominator of this difference quotient becomes 0. But it's okay for us if x isn't defined at x equals a, since we're interested in taking the limit as x goes to a anyway. So let's take the limit of both sides of this quantity, realizing that on the left we have the limit of f of x, and on the right we have the limit of a somewhat complicated expression. But the nice thing is that there are certain properties about limits that we can apply to simplify the right-hand side. In particular, the limit of a product is the product of the limits, provided they both exist, and in a similar way, the limit of the sum is the sum of the limits. Applying these results, we see that the right-hand side becomes the limit of the difference quotient times the limit of the quantity x minus a plus the limit of f of a. Let's look at each of these limits separately. The limit of the difference quotient we know. It's just the derivative of f at a by our computations we did earlier. And since our hypothesis is that f is differentiable at x equals a, we can replace this limit by f prime of a. This is the spot in our argument where we use the hypothesis that f is differentiable at x equals a. Now the next limit, the limit of the quantity x minus a, is just 0 since x is going to a. And the final limit, the limit of f of a, is just the constant f of a, since x doesn't appear anywhere in this expression. In total then, the right-hand side is f prime of a times 0 plus f of a, which is just f of a. Remembering that the left-hand side is the limit of f of x, we see that we can conclude that the limit of f of x is equal to the value f of a, which is exactly the property of being continuous. One important thing to note is that the reverse statement about continuity implying differentiability is not true, which is demonstrated by many examples, such as the absolute value function. Indeed, even though the absolute value function is continuous, it is not differentiable at x equals 0, as we've seen, since it doesn't have a well-defined slope there. One way of expressing this behavior is to say that the graph has a corner at x equals 0. Precisely what is meant by this is that the graph has one limiting slope from the left and another from the right. In this case, the limiting slope from the left is -1, but the limiting slope from the right is +1. Another way a function can fail to be differentiable is if its slopes approach a vertical line of tangency, that is, the slopes blow up to infinity, or to -infinity. For example, the function f of x equals x to the 1/3 power has a graph that looks like this, and from this graph it appears that the slopes are tending to infinity at the origin, that is, the origin should have a vertical line of tangency. Such behavior would make the function fail to be differentiable at x equals 0. Indeed, later on we'll compute the derivative of the function x to the 1/3 power, and we'll show that it's equal to f prime of x equals 1 over 3 times x to the 2/3 power, which, as x goes to 0, blows up to infinity, and isn't defined at x equals 0. This example demonstrates that the limit appearing in the definition of the derivative, namely the limit of the difference quotient, is supposed to be finite for the function to be called differentiable. And finally, it's important not to forget that a function can fail to be differentiable for an even more basic reason. It could fail to even be continuous, which, we've seen, is a requirement for being differentiable, according to the result we proved earlier.